Math 287, Quest to College. I'm Joe Vasta, and we are covering 7.3, Diagonalization. So let's go ahead and take a look at problem number 1. Find the eigenvalues of this matrix. Okay, so the first thing I'm going to do is write the A minus lambda I matrix. And I've got that one right there. And what do I have to do with that? To find the characteristic polynomial, I have to take the determinant of this. Now, the determinant of an upper triangular matrix, I think we had this theorem. It happens to be the product of the elements in the main diagonal. So let me go ahead and put the characteristic polynomial. 2 minus lambda, 3 minus lambda, 4 minus lambda. You set that equal to 0, and you get your lambda values 2, 3, 4. And so look at your main diagonal, 2, 3, 4. There certainly has to be a theorem that describes this, and there is. Theorem. If A is triangular, then its eigenvalues are the entries on the main diagonal. And so that gives us a great theorem that we will use later on in this lecture. Okay, so what do we have here? I'm having problems with the pointer on this thing. Okay, there it is. That's off. A happens to be the 2 by 2 matrix, 4, -5, 2, -3. Lambda 1 is -1, V1 is t times 1, 1, where t does not equal 0. I did not put that on this slide here. And lambda 2 equals 2, with its eigenvectors t, 5, 2. Now, if this looks familiar, this was our first example from the 7.1, 7.2 lecture. So we put the eigenvalue, eigenvector pairs up there next to the matrix. And now I'm going to introduce another matrix, matrix B. -2, 1, -4, 3. So we have something that I have labeled here as a theorem, but it's really a definition. Definition. A is similar to B if there exists an invertible matrix S such that B equals S inverse A S. Quite a complicated definition for similar. So A and B, you can have two matrices that are equal. You can have two matrices that are row equivalent. Well, now here's a third kind of thing that you can have, two matrices that are similar. So let's take a look at problem 2. Let S equal 3, -2, 2, -1. And S inverse, you can verify this is true, is what we have there, -1, 2, -2, 3. Verify that B equals S inverse AS. So what we're doing is we're verifying this up here, which would make A be similar to B. Okay, so we're just going to verify this. And these are some of the problems that people hate doing, like verify that this is true. You're not even finding the answer. You're just doing a verification. So let's go ahead and do some busy work here. S inverse AS. So I write those three matrices down. I'm going to go ahead and multiply the first two matrices together. So look, -4 plus 4 would give me a 0, 5 minus 6 would give me a -1, and so on. And so I just multiplied the first two matrices together and got this one right here. And now I'm going to multiply those two matrices together. And I end up getting -2, 1, -4, 3, which is exactly what matrix B is. So this was just a verification. And some of you may be wondering, well, you were given the S's, the S and the S inverse. How would you find out if two matrices are similar? We're not going to get into that in our homework, but we do need this definition to move on to diagonalization. So we need to know what this is. So we can say, so that equals B. We can say that A is similar to B. Well, think about this. Look at this little definition here. If you multiply both sides of this equation by S on the left and S inverse on the right, then you can write A equals something that has B in the middle and has a matrix and its inverse on both sides of it. So we could say when A is similar to B, that B is similar to A. So that's something we can say. And then here's kind of a dumb one, but I'm going to put it down anyway. A is similar to itself. So that's probably easy to verify because then your S and your S inverse will both be the identity, and it's easy to show that. So let's move on to the next slide. We have A and B, and we verified on the last slide that A is similar to B. Problem 3, we are going to ask to find the eigenvalues of B. I don't want this whole lecture to be on PowerPoint. I want to actually write out some things that you should know how to write out in your homework. So I'm going to turn this back over to me writing on a piece of paper, but we will come back to the PowerPoint a few times in this lecture. Find the eigenvalues of B. This is problem 3. So what I'm going to do is I'm going to write B minus lambda I. This is going to give me -2 minus lambda, 1, -4, 3 minus lambda. What I want to find is the determinant, B minus lambda I, and I'm going to go AD minus BC. So A times D is going to be lambda squared, and then we have, what do we have? 2 lambda and minus 3 lambda, so this is going to be negative lambda, and then minus 6. Okay, so that's AD minus BC. So minus a -4 is plus 4. So what does this give us? This gives us lambda squared minus lambda minus 2. There's our characteristic polynomial. And when I set the characteristic polynomial equal to 0, then that's called the characteristic equation. So let's see if we can solve that equation, probably by factoring. So factors of 2 that subtract can give you a 1. Well, that would be 1 and 2. And I'm going to have the plus on the 1 and the minus on the 2. So what does this give me when I set each of those equal to 0? I end up getting lambda equals -1 and positive 2. And so that completes problem number 3. Find the eigenvalues of B. Now back to the PowerPoint. So we were asked to find the eigenvalues of B, and I did it on a piece of paper. We ended up getting -1 and 2. Now what do you notice? The eigenvalues of matrix A are also -1 and 2. So is that just a weird coincidence? What I'm going to do is I'm going to go ahead and show you a theorem. And it says if A and B are similar, which we had, A and B are similar, then they have the same eigenvalues, including algebraic multiplicity. So that is a good theorem. That's going to help us get what we want, and we don't know what we want yet, I guess. Now, we got to do, we have to point this out because people are going to assume this. We cannot assume the converse, so I wrote it in red. The converse of an if-then statement. So this statement says if P, then Q. The converse is if Q, then P. So we're saying that this is the if part and that's the then part. Well, the converse is not always the same as the original theorem. Now, if it were, I'd put an if and only if and not put the if then. But let's just look at the converse, which is false. If A and B have the same eigenvalues, then they are similar. I'm going to go ahead and prove that this is not true. So sometimes when you want to prove something that is not true, you assume that it is true, and then you watch the universe collapse as you proceed with the proof. So I'm going to assume that the converse is true, and I'm going to come up with an example that blows up. So here's my example. The identity and this matrix, which I'm going to call C. Now look at both of these square matrices. They are both upper triangular, aren't they? The identity is also lower triangular as well. But I'll just say they're both upper triangular. So you could just look at the eigenvalues by looking at the main diagonal from that previous theorem. And both of those matrices have the same eigenvalues of 1 with algebraic multiplicity 2. Okay, so we have this if part of this converse, which is wrong. So A and B, well, now they're called I and C. I and C have the same eigenvalues. So are they similar? Let's take a look. The converse says I and C are similar, which means you can write C as an S inverse. So there's some matrix out there called S where you can go S inverse I S, and that equals C. Well, remember the identity is like the number 1, and when you multiply the identity times like S, you just get S. So is, or IS, is just S, and so that's what we have there. And then S inverse times S, well, that is just the identity. So what did we just show? We just showed that C equals I. Does C equal I? Absolutely not. So at the end we say, but C does not equal I. Therefore, the converse of this theorem right here is not true. So what we're going to do is we're going to move on because we want to talk about something with diagonal matrices. A diagonal matrix is both upper triangular and lower triangular. So matrix I is a diagonal matrix. So we have our matrix A here, and we have the eigenvalues, which are -1 and 2. This is the same one we've been looking at, and there's the eigenvectors of -1 and the eigenvectors that go with 2. A is non-defective. Now let's look at a definition, and this time I really do have it labeled correctly. If A is similar to a diagonal matrix, then A is diagonalizable. Try saying that. Okay, so we have a matrix that can be something called diagonalizable. It just means that matrix is similar to a diagonal matrix. So our question is this: is A diagonalizable? This is what they're going to ask you to do in your homework. So you might wonder, well, why aren't you just writing this on a piece of paper? Because we're going to do this problem sort of the long way. We don't know how to do this problem, so we're going to kind of develop a strategy for this problem. So we're going to suppose that it is. So let's just suppose A is diagonalizable. Then there exists a matrix S such that D, that's a diagonal matrix, equals S inverse AS. So it just says that A and D are similar. We're D is a diagonal matrix. Okay, so now we have A and D are similar, and we had a theorem that says if you have two matrices that are similar, they will have the same eigenvalues. So the last theorem says that both A and D have the same eigenvalues. So we already know the eigenvalues of A. They are -1 and 2. So the eigenvalues of D have to be -1 and 2, and not only that, but that -1 and 2 have to appear on the main diagonal of matrix D, our diagonal matrix. So I'll use that notation that we've used in the past. So let our diagonal matrix be diag -1, 2. What does this really mean? It means it's a 2 by 2 matrix, and it's -1, 0, 0, 2. That's what diag -1, 2 means. Okay, so now we know what matrix D looks like. We know what matrix A looks like. We don't know what matrix S looks like. So when you don't know something in math, you look 10 times smarter when you say, oh, my unknown is X. Well, we don't know what matrix S is, so we're going to actually look 40 times smarter by saying, let's let S be A, B, C, D. So we didn't know, we panicked, and we said that's what it's going to be. Now, I'm going to go ahead and rewrite this equation right here. Okay, and I don't like the S inverse in there, so I'm going to multiply both sides of the equation by matrix S on the left side of each of those terms there. So I have SD equals AS. Okay, let's go ahead and plug things in. So now the reason I did that is so I wouldn't have to do S inverse. I don't want to go S inverse and then put 1 over the determinant, so this is a lot cleaner. The other way is legitimate, but it's a little messier. So there it is. There's S, and then here's D. Here's A, our original matrix, and then there is S. Okay, so now what I'm going to do is I'm going to multiply the left-hand side together, and I'm going to multiply the right-hand side matrices together, and I end up getting this mess. I have a 2 by 2 matrix equals a 2 by 2 matrix, so that's going to yield 4 equations. I'll write those 4 equations below. Now, fortunately, these 2 equations just have A's and C's in them. And in fact, if you look at either equation, look at this. If you look at the top equation, you could subtract 4A on both sides, and you'd have -5A equals -5C, A equals C. If you add it on this bottom equation, 3C to both sides, you would have 2C equals 2A, C equals A. In any case, these two give you A equals C. Something similar is going to happen over here. Let's bring the 5D to the left on this top right equation. So then you'd have 5D and then bring that to the other side. So 5D equals 2B on that equation. And then down here you have the same thing, 5D equals 2B. So look what we have. A equals C, 5D equals 2B. You have infinitely many solutions that will work. You have infinitely many matrices S that you can actually write this out with. Now, I know this is still highly theoretical. We need one S. So why don't we just make A equal 1, C equal 1, and we'll make B equal 5 and D equal 2. So you'll have 10 equals 10. So that's what I'm going to do. So we only need to find one S, and so I have it. And look what I have here. Here's my S. That was the one we were trying to find. Here's A and C. We have the ones there, and then B and D. So here's 5, here's 2. Okay, so there it is. Now look at this PowerPoint slide. You might have to pause the video, and I kind of made it a little obvious what do you notice? Okay, so this is the thing that I'm trying to get you to see. Look up here. I made this eigenvalue eigenvector pair be in red. -1, look. And then right below on the S, there is the eigenvector 1, 1. And we could have actually used another eigenvector that was associated with -1. We could have used 5, 5 or 3, 3. And then look at this here. It's all lined up. 2 is an eigenvalue, and 5, 2 is one of its eigenvectors. Look, 2 is an eigenvalue. It's in matrix D. And matrix S holds the eigenvector. So maybe next time we're asked if a matrix is diagonalizable, then we can be a little bit smarter and not do all this. But we didn't know, so we had to do this. And now we see the pattern, and here is a theorem. A is diagonalizable if and only if A is non-defective. So that's how you check to see if something is diagonalizable. All you have to do is see if it's non-defective. We could also say A is not diagonalizable if and only if A is defective. That's the if and only if is strong. So that's going to make these problems, a lot simpler than what we did. And in fact, all the work, most of the work you'll be doing will be skills from 7.1 and 7.2. So let's go ahead and do some problems. And our first problem says, is the matrix diagonalizable, matrix A? If yes, find a matrix S and D such that D equals S inverse A S. And there's a matrix. So we're going to move this over to doing this on a piece of paper, and then we'll come back to the PowerPoint. Problem number 1. So we started our renumbering. Is the matrix diagonalizable? Okay. And we had a theorem that says a matrix is diagonalizable if and only if that matrix is non-defective. So we just have to check to see if this is non-defective. Now before I actually move on with this, let me show you a theorem that was not on the PowerPoint, but it is on the theorem sheet. Let A be diagonalizable. You have some eigenvalues, not necessarily distinct, so this could be 1, 1, and then 5, etc. And they are corresponding to the following set of linearly independent eigenvectors: v1, v2, yada yada yada, vn. Then D equals S inverse AS, where D equals diag, there's your eigenvalues in the order, and S is the columns. You put the eigenvectors corresponding to each eigenvalue in the columns. And so this is basically what we sort of derived through an example on the PowerPoint. And so we'll do that if this guy is diagonalizable. So let's go ahead and check this. Well, what kind of matrix is this? This matrix here, this is not a diagonal matrix. I almost said that. This is an upper triangular matrix. And we have that theorem that says, oh, well, we can find the eigenvalues really quickly. The eigenvalues are the main diagonal entries, 1 and 1. So lambda equals 1, and it has algebraic multiplicity of 2. So now the next thing I'm going to do is I'm going to go A minus lambda I. Now, if you actually have to write out, 1 minus lambda 2, 0, 1 minus lambda, you can. I'm just going to go ahead, and I think I can do this. So 1 minus 1 is 0. And then I have the 2. And then I have the 0. And then I have 1 minus 1, which is 0. Okay, so I do feel a little bad for doing that, in case you were lost on this. Lots of times when I have to find the eigenvalues, I'll start off by doing this. Sometimes I won't write it down, but I think this time I'll write it down just in case people got lost. And so I went ahead and put 1 in there, and I ended up zeroing out the main diagonal. This matrix is row equivalent to 0, 1, 0, 0. Now, what am I trying to find on this matrix? I already have the eigenvalue of 1. So I already have that. So I'm trying to find the eigenvectors. I find the eigenvectors by finding the null space of A minus lambda I. So there's a 0 there, 0 there. I'm finding the null space, 0 there and a 0 there. We'll call this X and Y. And X is free. Y is bound. Here's our tradition. There's the leading 1 there. So our top equation says y equals 0. And then x is free, so x is going to equal t. And our set of eigenvectors looks like this. It looks like t, comma, 0. So the eigenvectors look like this. T, and then we have 1, comma, 0. T does not equal 0. But what do you notice about this? If you had to write the eigenspace, it would be the span of 1, 0. But the dimension of the eigenspace, there's only one parameter, so that tells us the dimension of the eigenspace is 1. Or the geometric multiplicity is 1. Geometric multiplicity does not equal the algebraic multiplicity. Or we'll say it this way, algebraic multiplicity does not equal the geometric multiplicity, which tells us that A is defective, which tells us A is not diagonalizable. And that's what they wanted us to do. Okay, so most of this problem was skills from 7.1, 7.2. A is not diagonalizable. Now notice the follow-up question says, if yes. Well, ours was no. I mean, we could have just said no for our answer. So we don't have to do anything else. But think about this. Like, if you try to do something and say, oh, my diagonal matrix is 1, 0, 0, 1, because those are my eigenvalues, and then you try to create your matrix S, you would only have one eigenvector that you can put along the columns. I mean, you could, if you try to put another eigenvector along the columns, which was a multiple, then those two eigenvectors or those two columns would not be independent. So you couldn't do this when your matrix is defective. So that is how you do problem number 1. So this was the problem that we just did, problem number 1. And we found out lambda equals 1 has algebraic multiplicity 2, geometric multiplicity 1. So your matrix was defective. It was also not diagonalizable. So why don't we go ahead and take a look at another example. Problem number 2. Is the matrix diagonalizable? If yes, find a matrix S and D such that D equals S inverse AS. And there's your matrix. It is a 3 by 3 matrix. What are we really asking you to do? We're really asking to see if this matrix is defective or non-defective. And then once we get that, we'll know the answer immediately to the diagonalizable. So we'll go back to the paper. Is the matrix diagonalizable? Here's the matrix A. So let's go check this out. Really, we are trying to determine whether A is defective or non-defective. That's basically what they're kind of asking. So to figure that out, I have to find the eigenvalue, eigenvector pairs of this matrix. To find the eigenvalue, eigenvector pairs of this matrix, I must compute A minus lambda I. A minus lambda I is minus 2, or negative 2 minus lambda, and then we have 2, and then negative 3, and then we have 2, 1 minus lambda, negative 6, negative 1, negative 2, 0 minus lambda is negative lambda. So this matrix I'm going to refer to a few times. So I'll circle it in green. Okay, I want to find the eigenvalues. So I take the determinant of this matrix that I have circled in green and I set it equal to 0. And I'll set that thing equal to 0 in a little bit. I'm going to go ahead and run across the first row here. That's what I'm going to do. So a negative 2 minus lambda is in the positive position. So I write that down like that. And then I have to find its minor. And I'll take this a little slower here. So the minor is 1 minus lambda, negative 6, negative 2 minus lambda, the determinant of that matrix. And then we're running across. 2 is in the negative position, so I'm going to go minus 2 times its minor, which is 2, negative 6, negative 1, negative lambda. And then I get over to this element right here, which is in the positive position, so I'm going to go plus a minus 3, which is really minus 3, times its minor, 2, 1 minus lambda, negative 1, negative 2. Okay, we continue. This is minus 2 minus lambda, or negative 2 minus lambda. And then over here, what do I have? I have AD minus BC. So this is going to be negative lambda plus lambda squared. And then that's AD minus BC, so this is going to be minus 12. Then we have minus 2 times the determinant of this matrix. So this is minus 2 lambda, minus 6. And then we have minus 3 times the determinant of this matrix. We do have to be careful on this. Okay, so AD is negative 4 minus when you multiply these guys together. So if I multiply these guys together, I get negative 1 plus lambda. So this is really going to be plus 1 minus lambda. And of course, I'm going to need another piece of paper to continue here. This is all to find some eigenvalues. And what I'm doing here is stuff that we did in 7172. But there's, it's always good to see another problem worked out here. So what do I have here? I have negative 2 minus lambda. This guy is lambda squared minus lambda minus 12. I'm going to actually factor a negative 2 out of that. So this is going to become plus 4. And this is going to be lambda plus 3. And then I'm going to go minus 3. And then this is negative 3 minus lambda. Okay, now before I go ahead and multiply everything out and get a third degree polynomial, I do notice something here. I have a lambda plus 3 there. And then over here, I mean, even though it says negative lambda minus 3, I can factor a negative out of there and then get a lambda plus 3 right over there as well. So if I can see a lambda plus 3 here, then I don't have to multiply it all out and then perhaps even have to do synthetic division and all that. And I think, let's see what we get here. I have -2 minus lambda. Factors of 12 that subtract to give you 1, and that would be 3 and 4. So look, 3, 4, and the negative goes on the 4. So look at that. There's a lambda plus 3 there. Let me go ahead and write out these other terms here. And so I'm going to factor a -1 out of there and rearrange those terms. So this is going to be plus 3 lambda plus 3. Now see what we have there? We have a lambda plus 3. There are actually 3 terms on this line. The first term is that right there. The second term is this guy. And the third term is that guy. And each of those terms have a lambda plus 3. So I'm going to factor that to the front. So this is lambda plus 3. And we have what? What do we have? So left over here is -2 minus lambda times lambda minus 4. And then over here we have a plus 4. And then here is plus 3. Okay, I'm going to continue. We have lambda plus 3. Inside these brackets, I'm going to do a FOIL. So I'm going to get a negative, and I'm not going to do it in that order. I'm going to get a negative lambda squared. And then what do I have here? I have a 4 lambda minus 2 lambda, which is a 2 lambda. And then this gives me plus 8. And then that's plus 7. So this gives me lambda plus 3. And I'll change to parentheses now. Negative lambda squared plus 2 lambda plus 15. I'm going to factor a -1 out of that factor, and I'll bring it out in front of both of the factors. So this is going to be -1, and I'll just put a negative there, lambda plus 3. And then this thing becomes lambda squared minus 2 lambda minus 15. Okay. I'm going to see if I can factor this, because I'm setting this polynomial equal to 0 eventually. Negative lambda plus 3. Factors of... Oh, I lost my 1. Good thing I noticed that. Factors of 15 that subtract to give you 2. Well, that would be 3 and 5. And I need a -2, so I'll have -5 and plus 3. So what do we have here? We have negative lambda plus 3 squared, and then this is lambda minus 5. And this happens to be a minus lambda I. I set this thing equal to 0, and I end up getting -3 and positive 5. Those are my eigenvalues. I'm going to actually write 5 first. So I have lambda equals 5. Why did I write that first? Because that has algebraic multiplicity of 1. And lambda equals -3 has algebraic multiplicity of 2. Okay, so do I now know if my original matrix is defective? The answer is no, I don't know that yet. I have to figure that out by cranking out the eigenvectors. Okay, so I'm going to start off with lambda equals 5. Lambda equals 5. And it has algebraic multiplicity of 1. We're going to go A minus lambda I. And so we don't need this piece of paper. We do need this fact here, lambda equals -3, but after I finish lambda equals 5. What I do need is that green matrix there. So this is where it helps to be in class where there's lots of whiteboard space. But we don't have lots of whiteboard space, and we'll make do with this. A minus lambda I. Well, A minus 5i, and I like to write it this way. I'm writing up the green matrix. And so what do I have? I have negative 2 minus 5 is negative 7. 2, negative 3. The next one is 2. And then we have 1 minus 5 is negative 4. And then negative 6. The next one is going to be negative 1, negative 2. And we have negative lambda, which is negative 5. Okay. Sorry about that. So what do I have to find on this A minus lambda I matrix? I have to find the null space. I could put 3 red dots there, but you know, I'm not going to do that yet because what I want to do is reduce this matrix. So let's go ahead and reduce the matrix. The thing that I notice here is that I like this right here, this negative 1, negative 2, negative 5 to be my row 1. And I'm going to write it as 1, 2, 5. Now, if I multiply this, which was row 3, by negative 2 and add it to row 2 to give me the new row 2, I would end up getting a 0 there. So let's go ahead and write that down. 0. And then we'd have a negative 4 minus 4, that's a negative 8. And then this would be negative 10 minus 6 is negative 16. Just doing some row operations. Now if I go ahead and multiply this row by a negative 7 and add it to row 1, and that's going to become the row 3, I end up getting a positive 7 minus 7, which is 0. Then I end up getting 14 plus 2, 16. And then over here I end up getting positive 35 minus 3 is 32. And so notice row 2 and row 3, they are multiples of each other. And so we can zero out that, and we should expect that to happen with eigenvalues. We should expect infinitely many solutions when we're trying to find the null space of A minus lambda I. So I have 1, 2, 5, 0, 1, 2, 0, 0, 0. Lots of times in lecture I'll just say, oh, I did the row operations for you, but I felt this time we should just do everything by hand so you can see me struggling with this, so you can know, oh yeah, that's what happens when I do my homework. My variables, x, y, z, and what do I have here? I have bound, and z is free. So I'll write that down. Bound, free. Z is t. Second row gives me the equation y plus 2z, 2t, equals 0. So I end up getting y equals negative 2t. Okay, third equation, or actually first equation, which would say x plus 2y and then plus 5z, 5t equals 0. So I end up getting x, 5t minus 4t is t, and that goes to the other side as a negative t. So it looks like my set of eigenvectors is going to be negative t, negative 2t, and t. I'm going to actually factor out a t. I'm actually going to factor out a negative t, just so we can have more positive numbers in here. 1, 2, negative 1. And then I can kind of get rid of that negative. So I've got some results here. My results are this, and this will be my results page here. I have lambda equals 5. The set of eigenvectors looks like this. T, 1, 2, negative 1. T does not equal 0. The eigenspace would be the span of 1, 2, negative 1. The algebraic multiplicity, and we have that right there, algebraic multiplicity, was 1. And then the eigenspace has dimension 1, which means the geometric multiplicity is also 1. Okay, we'll put something similar for lambda equals, I think it was negative 3 that we did. Okay, so that's what we have. And I think for lambda equals negative 3, the algebraic multiplicity was 2. So we'll put something similar here. Okay, so we'll come back to the sheet and fill it in and then answer the question if the matrix is diagonalizable. Okay, so another piece of blank paper. We have lambda equals negative 3. The algebraic multiplicity, by the way, was 2. And so now what I want to do is I want to go a minus lambda I. A minus lambda I is this green matrix, and I'm going to put negative 3 in for lambda. So what I end up getting is negative 2 minus a negative 3, so this is going to be 1, 2, negative 3. And then 2, we put negative 3 there, we end up getting 4, negative 6. And then negative 1, negative 2, put a negative 3 right there, we end up getting 3. What am I trying to find on this matrix A minus lambda I? I'm trying to find the null space. What do you notice about this matrix? You notice that row 3 is just row 1 times negative 1, and row 2 is row 1 times 2. So all the rows are multiples of each other. If you reduce this matrix, you can rewrite it like 1, 2, negative 3, and then zeros everywhere else. And I'm trying to find the null space. So we'll make this x, y, z. Only one bound this time, the other two are free. So bound, free, free. So we know, because there's two frees, that the geometric multiplicity is going to be 2. We know that. So why don't we just go ahead and put that, but we didn't have to do that early. Z is t. Y is a different parameter, s. And the first equation says x plus 2y, so plus 2s, minus 3z minus 3t, this equals 0. So x equals negative 2s plus 3t. Okay, I don't want to lose my summary sheet here. Okay, so let's go ahead and write that as an ordered triple. The ordered triple is negative 2s plus 3t, comma, s, comma, t. There's the solution right there. Infinitely many solutions. Let's go ahead and splactor. We'll move this out of the way. when I splactor, I end up getting S, and what do we have? We have -2, comma 1, comma 0, plus T, 3, comma 0, comma 1. So there it is. Those are the set of eigenvectors. Let's go back to our summary sheet. And so for the summary sheet, you know what? I'm going to write them in the other order. Why not? I just want to emphasize the fact that I can write those in any order. So I could actually say the set of eigenvectors is, and I'm just doing this to be a stinker, you know, to confuse people, I guess. I don't know. I just want to emphasize you can write them in any order. So this is going to be T 3, 0, 1 plus S, and then S is -2, 1, 0. S and T not both 0. Okay, because then you'd have 0, 0, 0 for an eigenvector. We cannot have that. The eigenspace is the span of those two vectors. So this is 3, 0, 1 and -2, 1, 0. The algebraic multiplicity was 2. And remember what we said here, the geometric multiplicity was 2. We can see that the eigenspace has dimension 2. Algebraic multiplicity and geometric multiplicity for each eigenvalue, they are equal, which means our original matrix, gotta move some things out of the way, which is that guy right there, A happens to be non-defective. Okay, but that wasn't the question. What was the question? The question said, is the matrix diagonalizable? So from that theorem we can go to the conclusion. So everything that we've done up to what I'm about to write is a review from 7.1, 7.2. So that's what I'm saying. 7.3 is just going to be doing a lot of stuff you've done in the past. And now here's the new part. It's going to be more than just saying diagonalizable. There's going to be one more step. But A is, I'm getting sick of saying that word, diagonalizable. Now I wasn't able to say that word for the longest time. The first time I taught this class, I was like, diagonalize. I could not say it until I realized I can say diagonalizable by just saying diagonal. And you may have seen me pause after that. So I say diagonalizable. And so that helps me get through this. So now we have what we want. We have to find a matrix S and D and a matrix D such that this. So we have to find a D and an S such that that's going to work. So A being diagonalizable just means A is similar to a diagonal matrix. Now we have this theorem that says you can do it as long as you line things up. And I'm going to show you how I do this. So what I like to do is I like to say, okay, so I'm going to find matrix D, which is a diagonal matrix. We know the diagonal matrix is going to have the eigenvalues in there. Now you might say, well, there's only 2 eigenvalues, but we're going to count this one twice because the algebraic multiplicity was 2. So I'm going to go like this. I'm going to go 5, -3, -3, and then put zeros everywhere else. Now we can use that abbreviated notation that says diag, but I think this might be better right now. And then I'm going to come up with the S. Well, the S, we kind of derive this, is going to be a 3x3 matrix where I pick an eigenvector of 5, which is 1, 2, -1. 1, 2, -1. I can actually pick any eigenvector for this. I'm just going to pick the simplest one. I'm not going to go with 6, 12, -6. I'm just going to go with this one. And then look over here. I've got -3 is the next one. Well, -3 has two independent eigenvectors that I can use. And I'm going to go ahead and just put this first one here. So this is 3, 0, 1. And then -3 also has this eigenvector. This is -2, 1, 0. In fact, there's infinitely many eigenvectors there, and I went and just grabbed those because I know those are independent. Now, I don't have to compute S inverse and verify that this is true, but it is. Now, you might be thinking, well, Joe, are there more than one way to write your answer? Is there more than one way to write your answer? And the answer is yeah, look at this. So my diagonal matrix, I'm going to actually speed it up here. Could be diag 5, -3, -3. That's exactly what this is right here. And my matrix S could have been this. 1, 2, -1, and I could have switched around these columns here. So this is -2, 1, 0, and then 3, 0, 1. So this could have been your answer as well. Now, don't write both of them down. Just, go with one of them. And then something else that could have been your answer. You could have said, oh, well, no, I like my diagonal matrix to be this. Diag -3, -3, 5. Could you have done that? Yeah, as long as your matrix S has an eigenvector for -3 for the first column, an eigenvector for -3 for the second column, and an eigenvector for 5 for the third column. So, let's see, -3, -3. I'll just put those in the first two columns in any order. 3, 0, 1, -2, 1, 0. Okay, so we've finished that. And then the eigenvector for 5, I'll make it be 1, 2, -1. So this could have been a different answer. So you could have picked any three of these answers. There's more answers than that. So that finishes off this problem, which was a huge problem. Everything, I don't know, I'll just put my pen there. Everything above that pen, and those are those other pieces of paper that I used, that was what we did in 7.1.7.2. 7.3, we say, oh, non-defective means that it's diagonalizable, and then we can find an S and a D where this happens. So this is the new stuff right here. So there it is. What good is this? Well, I'll show you an application of this back on the PowerPoint. Is the matrix diagonalizable? And we got a yes, and we did all this work here where we found the eigenvalues and created matrix D and matrix S. And that was the one that I actually boxed, the first one. It wasn't the blue one or the purple one. So what I think we're going to do is show you an application of what we can do with this. So there's A, there's D, there's S from the last example. So one application, and sometimes this happens often, where you have to take a square matrix to a power. Now, to go A to the 10th, you don't just take each of these elements and raise them to the 10th power. You have to write 10 copies of A down and multiply them all out. Now, if you're a computer science major, that actually takes up a lot of program there. It takes up a lot of computation. So there's a quicker way we can take matrices to the power. Why would you take a matrix to a power? Just for fun. Or maybe you're into cryptography, and some of the cryptography demands that you take matrices to a power to encrypt or decrypt. So I'm going to show you something. This is going to be really cool. You do not have to do this in your homework. So here it goes. We know that D equals S inverse AS, okay, because A is diagonalizable. I'm going to go ahead and solve for A in this equation by multiplying both sides by S. Of course, both sides on the left by S, and then both sides on the right by S inverse. And then I'll have A all by itself, and then I'm going to actually put A on the left-hand side. So that does sound confusing, but that's what I end up getting. So our goal is to go a to the 10th. So let's write that out. A to the 10th equals SDS inverse to the 10th. Now what I'm going to do is I'm going to write that out 10 times. You might think that I'm crazy, but I am the math teacher, so of course that goes with the territory. So I wrote that out 10 times. 3, 4, 5, 6, 7, 8, 9, 10. Okay, I was just counting to make sure that I had 10 of them. So that's a lot. But what do you notice? Look at this. There's an S inverse S. What is S inverse S? Isn't that just the identity? And then look here. S inverse S. S inverse S. S inverse S. And it just keeps going. So this can be simplified to S times D. Okay, there's probably a song that goes with this, but I don't have it. And that identity is just like a 1. So you really just have D times D times D times D, which is really D to the 10th power. So A to the 10th is S times a diagonal matrix to the 10th power times S inverse. Okay. We need S inverse. So I went ahead, I didn't show you all the details, but there's an expression for S inverse, and you can verify that. And now I'm going to go ahead. I know what S is. I know what S inverse is the one that just popped up on this slide, and then D to the 10th. Now, why do we like D to the 10th better than A to the 10th? You might already know. So what we have here is matrix multiplication. This matrix is to the 10th, but if you have a diagonal matrix and raise it to a power, because it's diagonal, you just have to raise each of the entries on the main diagonal to the 10th power, and that's how you can do a power of a diagonal matrix, and that's what I'm going to do. So instead of going A times A times A times A times A times, okay, instead of doing that, which takes a lot of computations, if we did this, then you're only multiplying, doing matrix multiplication 2 times, and then multiplying by the scalar 1/8. I'll spare you all the details of that. I ended up getting that for my 3×3 matrix. I have just taken A. This is A to the 10th power. So in cryptography, sometimes it's more than the 10th power. It could be the 50th power, the 64th power, or even to the 100th power. And you really don't want to start making the computer do all those matrix multiplications. If your matrix is diagonalizable, then life is a lot easier. I'm going to switch this back over to the paper. There's one important thing I want to tell you about one of the problems in your homework, and then I'm going to do something else that is completely optional, but all the math majors might want to stick around and watch that part of the video. So back to the paper. Okay, so you might get something like this in your homework, where you have some imaginary numbers in the matrix, and those are not fun to deal with. And I've seen some people take a problem like this. It says 1 minus I, and there's a 0, 0, 2, 1 plus I, etc. I'm not going to write out all that. And people will just go ahead and just make a big mess of this problem. You're trying to reduce it to row echelon form. And so look at the first row. It says 1 minus I, 0, 0. So a quick way of making this problem easier is multiplying by the scalar 1 over 1 minus I. And so I get a row equivalent matrix. Look at the first row then. It is 1, 0, 0. Now, I really couldn't have done that if there were like other non-zero numbers there. Then there would have been some consequences. But I know there's at least one homework problem where if you do this, you can make your algebra or your arithmetic of the matrices a lot easier. So let me just finish writing this here. Okay, the other thing that I'm going to do, and I wasn't going to do this, so a lot of you could just flip the video off. I mean, please don't flip off your computer. You can turn the video off. I don't know why I used the word flip. But for the math majors and other people who are interested in this, we have this interesting kind of problem, which gives us another good application of diagonalization. And you might be thinking, what? Another application? And it doesn't even seem like an application because I'm just doing this weird problem. Remember those problems from 7.1, 7.2, and even 7.3? We give you the matrix, and you are to find the eigenvalue eigenvector pairs. Well, I'm doing it the other way around. I'm giving you eigenvalue eigenvector pairs, and you are to find the matrix. Okay, so this is a little tricky. But how tricky is it? Okay, well, we're going to figure this out. First of all, it's a 2x2 matrix, so each of these eigenvalues have algebraic multiplicity 1 and geometric multiplicity 1, which means A is diagonalizable. I'm not going to write out that whole word. Okay. If A is diagonalizable, there exists a matrix D and S such that this happens. D equals S inverse AS. Okay? So I'm going to multiply both sides by S inverse on the left and multiply both sides of this equation by S on the right. Okay, so that was not a good thing to do. I have some white out now. Let me go find the white out. Here it is. I'm going to multiply both sides of this matrix. Oh yeah, not much of a fit there. By S on the left and S inverse on the right. Okay, so watch what happens. And I was doing this on the PowerPoint, but I didn't show all this. So I end up getting S times D times S inverse, and then over here that becomes the identity, S times S inverse, and then S times S inverse becomes the identity, and I get A on the right hand side. So I really end up getting this, A equals S times D times S inverse. And this is how I take A to a very high power. Now I don't know what A is, but you know what? I know what the diagonal matrix is, or what a diagonal matrix is. There's many choices that there's not many choices, more than one choice. My diagonal matrix, along the main diagonal, I have to have the eigenvalues. So I'll have the eigenvalue, I'll put 1 there and 7 there. Now I could have done this problem the other way and put the 7 on the top and the 1 on the bottom. There's the diagonal matrix. I also know matrix S, which happens to be the eigenvectors of those eigenvalues. So the eigenvector, one of the eigenvectors of lambda equals 1 is 1, 5. So I'll put that there, 1, 5. And then an eigenvector of 7 is negative 1, 1. S inverse is 1 over the determinant, that's 1 over 6. I switch my A and D, or switch my D and A, so those are switched, and negate my B and C. Okay, so I have the 3 matrices that I need. Now I'm going to figure out what A is. So A is S 1, negative 1, 5, 1. D 1, 0, 0, 7. And S inverse, I'll keep the 1, 6 right there. I don't want to bring it in for some reason. And then I have 1, 1, negative 5, 1. I'll bring it in at the end, okay? So that negative 1, 6 can creep out front. I'll just keep it right there for now. And then I'm going to multiply the first 2 matrices together. So I get 1, and then the next one is negative 7, and then 5, and then 7. That's by multiplying the first two matrices together. Here's the 1/6. 1, 1, -5, 1. Now, the 1/6 probably should have gone out front, but oh well. I'm going to go ahead and multiply those two matrices together. The 1/6 is like, I'm out of here. So he jumps out to the front. And now I have to be a little more careful because, you know, up here it was easier multiplying a diagonal matrix times another matrix. So looks like I have 1 plus 35, which is 36. 1 minus 7 is -6. 5 minus 35 is -30. And then the last one is 5 plus 7 is 12. Now I'm going to go ahead and bring the 1/6 in, and I end up getting the matrix 6, -1, -5, and +2. And so there was an application, even though you're like, well, I didn't see how this application like achieves world peace or anything. Well, it doesn't, but this application says that if you are trying to look for a matrix that has certain eigenvalues and eigenvectors, you can use this theory of the matrix being diagonalizable to get what you need. Now, I guarantee you, you can do this on your own. Go ahead and check this out. Go call this thing A, which is, that's what it is, and go A minus lambda I, cover this up, and you will get that as a result. So that concludes 7.3. There is another application that I will put in the PDF, and it has to do with Fibonacci numbers. I'm not going to go over it right now. You guys do your homework. Have a good day. I'll see you in the next video.